So, in this lecture, we're going to be discussing a topic that's related, but not quite directly related, to the previous two videos on integrating and differentiating vector-valued functions of a single real parameter. So, we're going to be talking about something that's, well, a very classical topic in analysis. Basically, we're given a bunch of continuous functions, a sequence of them, and we want to know if when we add them all up, this infinite number of functions, if we get a continuous function in the end, or if this function that we get is differentiable, or we want to compute its derivative in terms of the terms we're summing up. And we're going to start with this question of convergence of the series, not derivatives. And for this, we have this Weierstrass M test, which gives us a sufficient condition for convergence of the series of functions. We'll see as two consequences of that power series, as we know, are well-behaved functions, and also that there exists a function on the unit interval that is continuous but not differentiable at any point. Then we're going to go to derivatives, and we're going to see that under certain conditions we can prove that the derivative of the limit is the limit of the derivative, or equivalently, if f is given by an infinite sum of continuous functions with continuous derivatives, and these derivatives are suitably small, or they add up to something that's not infinite, then we can say that the limit is differentiable and the derivative of the series is the series of the derivatives. And as I mentioned, we're going to apply all of that to power series, which are kind of a very classical topic. We're going to see that by using these criteria, we have very direct proofs and perhaps very understandable proofs, very clear proofs of classical things about differentiating power series. Okay. So our setup for the time being for this general convergence theorem is a setup of functions from a compact metric space to a Banach space. Continuous functions, of course. And as we know, this space can be given a norm, and this is the norm. And this norm makes the space a Banach space, right? We proved even something more general about functions from compact to complete metric spaces. And then we have a metric that makes it a complete metric space. This norm is related to the metric, therefore the space is Banach, right? What does it mean to say it's Banach? Well, it means it's complete, and also it's a vector space, right? So we can naturally add up continuous functions from k to w and get another continuous function. Okay, so what's the question that we have? Suppose that you have the sequence of continuous functions here, these f sub n's. When is it the case that when I add them all up, I get an element of c, another continuous function from k to w? And in general, this is a very hard problem, but Weierstrass proved this theorem. He proved it in a kind of more specific context. But in current language, we can state it, as follows, that if your sequence of functions is such that the sum of the norms is finite, then the sum of the series is well defined, the same that you take the sum from n equals 1 to k. When k goes to infinity, this converges uniformly to an element f of the space of continuous functions from k to w. So that's Weierstrass M test, and it's a very clear criterion. When it applies, it's usually not difficult to use, as we're going to see. But it turns out that there is nothing too specific about continuous functions here. So I want to prove this theorem, this statement, as a consequence of a more general fact about complete metric spaces. And this is a fact that we're going to use. A metric space is complete, right? So x with distance d sub x is complete if and only if you have whenever you have a sequence of elements of x, and the sum of the distances between consecutive terms converges, then the sequence converges. So this is a criterion. I claim this condition, right? This condition that for all sequences with summable differences between consecutive terms, they converge. I claim that this is equivalent to completeness, but we only need one direction of this to prove Weierstrass's theorem. So we're going to prove this direction that says when it's complete, then we have this property. And the other direction is going to be an exercise in your homework assignment. Okay, so how do we prove this? Right, so let me notice that, okay, so I have my sequence with this condition that the sum of the distances between consecutive terms is finite. So let me define epsilon sub n as the tail of the series. That is the sum for m greater than or equal to n of dx sub m, x sub m plus 1. We're forgetting the subscript here. d sub x. Of course, this is defined for all natural numbers n. And the point is that this epsilon n goes to 0, as in goes to infinity, because we have here the tail of a convergent series. Right, so, and the point is that from this, we can bound the distance between, from these numbers are getting smaller and smaller, I can bound the distance between x sub n and x sub m. So, okay, now let me notice that for all m, okay, let me use a different index here, just because I don't want to mix up n, right? So this is still the same thing. So now take an index m that's larger than n, and I claim that the distance between x sub n and x sub m is upper bounded by this epsilon sub n. How do we do that? Well, let me just say that by the triangle inequality, I can bound this distance by looking at, right, the distance between x sub m and x sub n. M is the largest. So if m equals n, then there's nothing to do. So let me assume that m is larger than n. So I'm just going to say, well, you can bound this distance by only looking at consecutive terms, right? Plus plus dx xn plus 1 x sub n. Well, if you like, this is at the distance. If you prefer something slightly more formally written, then you can write this as a distance from j equals n to m minus 1 d sub x sub j plus 1, right? I'm using symmetry of the distance, but of course we know that's true. Now notice that this last sum that I wrote is a piece of the sum defining epsilon sub n, right? So epsilon sub n is not the sum from j equals n to m minus 1, it's a sum from j equals n to infinity. And because all the terms in the sum of epsilon sub n are non-negative, right, they're all distances, it's clear that the sum I have over here is upper bounded by epsilon sub n. Right? So what am I saying here? I'm saying that if I take a very large n and then an m that's even larger than n, then the distance between x sub m and x sub n is uniformly bounded by this epsilon n, which is a small number, right? Epsilon sub n is going to 0. My claim is that in fact we can prove to this that that the sequence is Cauchy, right? So that the sequence x sub n is Cauchy. So if I take now, right, let me add this. If I take a positive epsilon, take n naught in n such that epsilon n is less or equal to epsilon for all n greater than n naught. This exists because, right, this guy exists because of this, right? So because epsilon sub n is going to 0, at some point it becomes smaller than epsilon. And then the point to notice is that And for all m and n greater natural numbers, if both are greater than n naught, then the distance between x sub n and x sub m has to be less than epsilon. Well, how do we derive this thing here? How do we prove this? Well, okay, take m and n, they're greater than n naught. So either they're both equal, m and n, and then the distance is 0, and we're done. Or one is greater than the other. Say that m is greater than n, and then we can use this previous bound here, right? So there was one that gave us the distance is less than epsilon sub n. And then we say, well, distance between xm and xn is less than epsilon sub n. But epsilon sub n, because n is greater than n naught, is less than epsilon. So we're done, right? So we've shown that for each epsilon, there is an n naught that we can choose, such that the distances between terms of the sequence after n naught are always less than or equal to epsilon. And this means there is sequence x sub n is Cauchy. And we assume there are metric space x, distance x is complete. And this is what we need to show to prove convergence. Since the sequence x sub n is Cauchy, we've just shown it to be Cauchy, then we know that it's convergent. So this is the general result about metric spaces that I want to prove, that in a complete metric space, for a sequence to converge, it's sufficient that the sum of distances between consecutive terms is finite. How do we use that to prove this Weierstrass-Imtest theorem? Well, we just need to adapt this to a setting. I'm just going to define S sub k to be the partial sum from n equals 1, could be n equals 0, doesn't make too much of a difference, f sub n. This is an element of C. And we notice that the distance, right, so if you use the metric in this space C, the distance between consecutive terms of the sequence, right, so this is defined for all k and n. The distance between consecutive terms is just the difference between s sub k and s sub k plus 1, the norm of this. And this is precisely the norm of function f sub k infinity. Now, our assumption is such that the sum of these distances, right, before the index was n, now it's k, but it doesn't matter. So the sum of these guys is just the sum of the norms of the f sub k plus 1, sorry. And this sum is finite. Therefore, by the previous exercise, there exists a limit of s sub k, right? S sub k converges to somebody. And this limit is precisely the function f that we're looking for. Okay, to recap. So I want to apply this general result about complete metric spaces. We are in a complete metric space because this guy is Banach. So what do? I define these partial sums of the functions f sub n. And I notice that the distance between consecutive terms of the partial sums is just one of the functions, s sub k plus 1. Let me write this properly here. Now, when I add up the distances, I get the sum of the norms of the f sub k or f sub n, and that's finite. That's our assumption. And therefore, by the previous result, we know that s sub k has to converge to somewhere. It converges to this f, and that's precisely what we wanted to show. It converges according to the norm of the space, or the metric, if you like. Therefore, we have shown Weierstrass-Imtest. How is this test useful? Okay, first application is to power series, which of course we all know from calculus and from complex analysis. Here I'm doing the real version. The complex version, you need to work a little bit harder, but it's really not much different, right? So what's a real version? Well, my point is to make sense. My goal is to make sense of this expression over here. And I want to know that it makes sense and defines a continuous function over this interval from t naught. T naught is just the center of the power series. t naught minus capital R to t naught plus R. I want this to be a continuous function from this interval to the real line. And I claim that this condition over here is sufficient. How do I prove that? Well, I'm going to apply the m-test to the terms of the series f sub n of t n. And notice, okay, right? So these are the individual functions. And of course, this is defined for t in our interval. So the individual functions are continuous because they're polynomials. I mean, there's nothing to be proven here. So what's the norm of f sub n? Well, that's easy. Well, if you look, there's a sub n, and that's just a constant pops out outside. And then I have t minus t naught raised to n. I need to take the sup of the absolute value in this interval from t naught minus r to t naught plus r. And it's really easy to show that this sup is simply r to the n. And what does this give us? Well, okay, so we know that one of the ways in which we can show that a series converges is to look at the root test, or to take the root test. We take the 1/nth root of the nth term, right? And if we show that that's less than 1, then the lim sup's less than 1, and then we are done, right? So what's the lim sup of the nth root of the norm? Well, that's simply, well, okay, what's the nth root of the norm? That's a sub n 1/n times r. Therefore, if I look at the sum of the norms of the f sub n's, that's finite, because that's just a good old, right? That's just testing the convergence of a sequence of real numbers. So that's the import of Weierstrass test. It turns a difficult problem and converts a series into an easy problem. Converts a series of functions. It turns it into convergence of series of real numbers. And because this lim sup of norm of f sub n raised to 1/n, where we look at the assumptions, right? So this is the guy over here. We can see that lim sup of this thing is less than 1. And if the lim sup of the nth term of the series, 1/nth root of that, is less than 1, then the series converges, which is what over here. And as we know, that's sufficient to imply that there's a continuous function, like this one here, that is the limit of the sum of the f sub n's. So we've proven that power series converge. We'll later show, by using related tools, that not only does the series converge, but also the derivative of the series is what you expect it to be. You can just differentiate term by term of the series. But now I want to do something different. I want to show you an example that's also due to Weierstrass. So he's the main guy in our lecture today. So Weierstrass, a long time ago, he proved something that sort of shocked the mathematical world, though there were kind of, maybe somebody else like Bolzano had proven it before. But he proved that there are continuous functions that don't really have derivatives anywhere. So interestingly enough, there had been some degree of argument about what constituted a function. The modern definition of a function is due to Dirichlet, just saying any rule that associates values in a domain to values in a counter domain. Of course, that's kind of a modern but intuitive version. The less intuitive version using set theory still had to wait for some years. But and it was clear at the time that, there are functions that are not continuous. Like the function that maps each rational number to 1 and each irrational number to 0, that cannot be continuous. However, it was sort of believed that if a function is continuous, it cannot be too complicated. Well, maybe it's not differentiable at some cusp points, like this function that's drawn the slide, right? This function is called phi, by the way. So phi is not differentiable everywhere because there are these cusp points, these points where it's not differentiable. However, it's differentiable almost everywhere, right? And it sort of stretched the imagination of people at that time to think that maybe it was a continuous function that was not differentiable anywhere. And that's what Weierstrass built. He actually built a variant of this example that I'm going to present. So this example not due to him. He showed that there is a series of differentiable functions whose limit is nowhere differentiable. So here we're doing something weaker because the terms in our series are not differentiable everywhere. They're just differentiable at most points. Okay, what is this function f that's not differentiable anywhere? Okay, here are the building blocks. I'm going to take these functions f sub n of t, which you remember the phi from the previous slide. Okay, the building block is this. This phi is just a function that's, well, it has this tent shape over the interval from 0 to a half, and then you make it 2 periodic. You define it over the rest of the real line so that it has period 2. So it's just a sequence of tens going in both directions, left and right. The f sub n's are rescaled versions of of phi, but we were rescaling inside the function. So when you take this 4 to the n times t, you're making the graph of phi narrower, right? So it's as if you have this sawtooth construction, but instead of having these long things, you have very narrow kind of teeth. But I'm also decreasing the amplitude, so to speak, of the sawtooth. I'm also multiplying it by a factor that's less than 1. And that by itself is enough to show that the sum of the f sub n's defines a continuous function. Why is that? Well, the phi from the previous slide takes values between 0 and 1. Therefore, its norm is 1. So the norm of f sub n is 3/4 to the n, and clearly since 3/4 is less than 1, the sum of the norms is finite, right? So that's just a sum of arithmetic progression with ratio less than 1. And by the m-test, that means that the sum of the f's of n's is a continuous function over any interval that you like. It's actually, so it's actually defined over the real line, the entire real line, but I'm just saying, well, it defines a continuous function over any interval a, b that you choose. And here's the claim that we're going to show. I'm going to show that this function is non-differentiable. It's non-differentiable because it has infinite slope in some sense. So for any point in the real line, I can find a sequence of h's going to 0, such that if I look at the quotient, that should give me the derivative of the limit, right? So f of t plus h sub m minus f of t divided by h sub m. Right, so when h goes to 0, h sub m goes to 0, but this quotient goes to infinity. And clearly, if that's the case, the function is not differentiable, right? So if the function was differentiable at t, then I could take this quotient would converge to the derivative, but then if the claim is true, there's no derivative. And actually, because I want the notation to agree with the next slides, let me switch from t to x, because they think that's what I have here. Okay, so I want to prove this claim, and I want to prove that this function f, that's the sum of the f sub n's, is nowhere differentiable. So for that, I have to estimate this quotient, and the quotient will be defined, right? So the h sub m's are always going to have this form. They're either going to be plus 4 to the minus n times a half, or minus that. Why this choice? Okay, first of all, we need a preliminary fact, which is that this building block, this function, the sawtooth function, phi, is 1 Lipschitz. That's related to the fact, that's an exercise for you. I'm not going to prove it. Otherwise we'd spend too much time on this example. So this is a consequence of the fact that the derivative of phi, remember phi is a sawtooth, right? So the derivative has modulus 1 or wherever it exists. And also phi is continuous. So with these two things, you can prove this 1 Lipschitz property. Okay, so I said I would define h sub m to be either plus or minus a half times 4 to the minus n. Why do I do that? as we're going to see, that we do that to have a kind of a very specific effect over this quotient here. And this effect is related to, the difficulty in computing this quotient is that f is given by a complicated series. So I need to be a little bit careful here. So I need to make a wise choice of h sub m so that I am able to compute this. Okay, what am I going to do? So here you have a drawing. So I have this quantity here, psi of m, and that's the absolute value of h sub m, which I'm still going to choose. And the important thing for us is that 4 to the m times psi of m, right, so is equal to a half. So if you look at this interval from, okay, here I have 4 to the mx minus psi of m. What is that? Well, when I'm 4 to the mx minus a half, right? Because psi of m times 4 to the m is a half. And the same on this side, 4 to the mx plus a half is 4 to the m times x plus psi of m. In this interval, I can have at most one integer, right? Why is that? Because this interval is an open interval of length 1, so it cannot contain two integers. How is this useful? Well, I claim that either this interval, this open interval here, has no integers, or this one has no integers, and that you can easily check. So in this case here, no integers. In this case, I take h sub m to be equal to minus x sub m. If this is a guy with no integers, of course it could be that both have no integers, in which case I'm free to choose whichever one I like. H sub m is going to be, h sub m is going to be plus psi of m. Okay, so that's how I make our choice. We choose h sub m so that the interval 4 to the m, between 4 to the mx and 4 to the m times x plus h sub m has no integers. And this is going to be important because in these intervals containing no integers, we know how to define psi. Psi is just a function with slope equal to 1. Okay? Right, so well, now let's try to compute the quotient, right? So, and I'm going to do that term by term in my series. So recall that the individual functions in my series are these guys here. And I'm going to compute the quotient, the quotient for the derivative, right? So this is h sub m, h sub m. I'm going to compute that quotient for each individual terms, and then I'm going to try to add things up to show that everything works, okay? So there are three cases to consider here. First is a case where n is equal to m, is greater than m. And what happens in this case? Well, in this case, what is f sub n h plus x sub m? Well, that's f of sub n of x plus or minus. Remember that this guy here, it's a half. Sorry, let me write it. 3/4 of n psi of 4 to the n x plus or minus 4 to the n minus m over 2. Right? Remember that h sub m is always 4 to the minus n divided by 2 in absolute value. So it's one of these two values. So this is equal, if you like, to 3/4 n times psi of 4 to the n x plus a power of 2, plus or minus a power of 2. So notice that here I'm strongly using the fact that n is greater than m. So this is 4 raised to a positive number. So it's 2 raised to a number greater than, right? So let me put it like this. So this is 2 raised to 2 to the n minus m plus 1. Right? So that's the exact power of 2 you get. And this guy here has to be larger than 1. So this is an even integer. Right, because n is greater than m, so this exponent is at least, I guess, 5 actually. It's an even integer anyhow. And that means that this is equal to 3/4 to the n psi to the 4 n x, which is f sub n of x, because the function phi is 2 periodic. So I said before that if you compute phi at a point and phi at that point plus 2, that should give you the same value. Therefore, if for all k in z and for all t in r, right, so let me put this inside a blob. I have that phi of t is equal to phi of t plus 2 times k. Okay, and what did I just show? I just argued that if I'm going to compute f sub n of x plus hm for n greater than m, then I'm always computing, basically up to rescaling here, I'm computing phi or 4 to the n plus x, plus or minus an even integer, and that's the same as computing at x itself, which will give me f sub n of x. Therefore, when I take the quotient, this includes a difference. My claim then is that this guy is simply 0. In this case we're considering. So the quotient, if you take n that's small, meaning smaller, this is this correct? Yes, of course. If you take n, large, then this term simply vanishes. I'm just looking, right? So if n is large, then this term gamma nm vanishes. Okay. Sorry, I'm missing a page here. So let me create a page. No, that's not what I should be doing. And now you're seeing me make a fool of myself. Insert page, and hopefully that's going to be enough. Yes, so now I'm going to consider the other cases. So what happens when n equals m? In this case, I have that f sub n of x plus, right? Remember I chose h sub m, right? So in this case I have f sub m of x plus h sub m. What is this? This is 3/4 of n in of phi of 4 to the m x plus h sub m. And I have f sub m x is the same thing, but only with x. So notice and remember that we chose h sub m so that there are no integers between x plus h sub m, 4 times m, and I have 4 times m x. What does that mean in terms of the graph of the function? Well, it means the following. So here I have x, and let's say that h sub m is positive. So remember that our function psi, it has this sawtooth shape, and the sawtooth only changes, so to speak, at the integer point. So in this interval from x to x sub h sub m, the function phi has constant slope equal to 1. Right? It could be going down as I drew first, could be going up as I drew second, but in either case, that if you look at the absolute value of the difference, well, that's 3/4 to the m times the difference between phi and absolute value and of course this is equal, right? It said the slope is 1, so it's just a difference between these two guys. So it's 3 to the m times, 3 to the m, 4 to the minus m, times the difference between these guys in absolute value, which is just h sub m. And now so when we look at the quotient, right, this guy is going to drop out. Oh, sorry, there's a h sub m times 4 to the m, right? So that's important for us, because 4 to the m, the distance between 4 to the mx plus h sub m and 4 to the mx is h sub m times 4 to the m, and the distance is just an absolute value. So this guy cancels, this guy cancels. The quotient that we get, therefore, right? So to compute the quotient, remember this guy is simply fn of h plus x sub m, well, fm, minus f mx divided by h sub n, m. So the h sub m drops out from the calculation when I divide by it, and I get simply 3 to the m. So we see, right, so beginning to get an inkling of what's going to happen. Remember, we want to argue that the coefficient here goes to infinity. And the coefficient is a sum of, not coefficient, sorry, the quotient. And the quotient is a sum of quotients coming from the f sub n's. And we just found out that one of these quotients is very large, right? This is what we have over here. It's 3 to the m. And now I'm going to need to create a new page again. Sorry about that. Yeah. Because we still have the case where n is less than m. Right? So that's the last quotient we need to define. So for this case, we're going to just make it simple. I'm just going to notice I'm computing 4 to the n. Sorry, that's f of n of x plus h sub n, m minus f of n x plus x. Well, that's divided by h sub m. Well, that's at most, well, that's equal, in fact, right? By the way, this is the quotient gamma, sorry, I need to look it up. Gamma n m. So this quotient is going to compute it just by computing using the Lipschitz function, the Lipschitz constant of psi, because this is psi of 4 to the n x plus 4 to the n h sub m minus psi of 4 to the n x divided by h sub n m. And here, right, the thing on top, we argued right in the beginning that it was 1 Lipschitz. So I can bound the distance between these two guys by the distance between the arguments of the function. So I get 3/4 of n times 4 to the n modulus of h sub m divided by the modulus of h sub m, and that's 3 to the n. So I finally arrived at our formula, because I can write this like this. That's the sum from n equals 1 to infinity of, right? So if I look at the definition of the function, f sub n h plus h sub n, so I want the modulus here, minus f sub n h sub m. Sorry. So remember that these quotients, right, what do we know about them? So for n greater than m, they're 0. And the other ones we know how to compute. So I'm just going to say, okay, first consider n equals m, right? That's the case we covered here. We got exactly 3 to the m. So let's equate m minus the sum of n equals 1 to m minus 1s, right? So that's going to be this case, psi n m. And in this, so we're going to get, well, this guy, this guy over here, gamma of mm, is simply 3 to the m, and the other ones are 3 to the n. And now we just have to argue that this number, well, we can compute it explicitly. I'm not going to do it here just because I'm lazy. But this number, when m goes to infinity, it goes to infinity. Basically, what I'm using here is that I have this geometric progression. So, right, so the sum of these guys, I can write, I'm going to write it explicitly. It's just 3 to the m minus 1 divided by 2. And I just look at these things and I see that they're gonna go to infinity. So we're done. We've looked at the quotient, right? So here we have it. Sorry, I should have made this more explicitly. I needed to look at the quotient for f, and I broke it down in terms of the quotients for fn, which are these gamma m n that I computed before. So most of them are 0, so once n gets larger than m, they're all 0. At m, they're equal to 3 to the m. At larger numbers, they're at most 3 to the n. At smaller numbers, sorry, they're at most 3 to the n. And that's how we get our calculation to work. So we see it's a bit of a convoluted example, but in case it wasn't clear, right? So we used the fact that phi is 1 Lipschitz at some point, but how did we use this choice of h sub m? We used it because we wanted to compute exactly this coefficient here, this gamma mm, right? This gamma mm. We wanted to compute it, and in order to compute it, we wanted to say, well, since there are no integers between 4 to the m x plus h sub m and 4 to the m x, I know that the slope of phi in the corresponding interval is 1, and I could do an exact calculation. So, and in other points, we're happy to either say, well, it gives you 0, or it gives you something less than or equal to the 3 to the n. And that's what we needed to prove that the quotients go to infinity. Okay, great. So now you've learned a classical topic and analysis. There are functions, they are nowhere differentiable. And by the way, if you remember the problem in the exam where you're asked to show that the set of functions that are differentiable at a half has empty interior and full closure, the same is true about nowhere differentiable functions. They have empty, the same is true about nowhere differentiable functions. They have empty interior and full closure. In fact, I mean, there's a lot more that's known about them. Sometimes they constitute the majority of continuous functions, but I'm not going to get into that. Okay, so now we get to the topic of derivatives. And remember, we had this set up where taking functions f sub n and looking at the series, that's the sum of them. So because I want to talk about derivatives, and up to now we've only been able to differentiate functions of a single real parameter, I'm going to specialize to the setting where instead of a general compact metric space, I have an interval in the real line. And I want to ask the following question. Suppose I have differentiable functions in this space, and I know that their sum gives me a continuous function. Does it follow that this continuous function is differentiable? Or even, does it follow the stronger statement that I can add up the derivatives of the series and get the derivative of f? Well, the answer is that in general is no. And in fact, Weierstrass, that's the W here, when he gave the example of a continuous function that's nowhere differentiable, he had an example that of exactly that kind. So he showed that a series like this, a to the n cosine of b to the n gamma t, is continuous and nowhere differentiable. And for that he needs a condition like a times b, so a less than 1, b is a positive integer, and a times b is greater than something like, I think, 3 pi over 2. So for some choice of a and b, this function is continuous and nowhere differentiable. It's actually a nice exercise to show that this function is continuous. That's just an application of the m-test. But this serves the purpose of saying, okay, maybe you're adding up differentiable functions, but there's no way to know whether the limit is differentiable. Not from general statements like this. However, there is a criterion. And that's theorem 2. So theorem 2 says the following. Suppose you have differentiable functions from a, b to w. W is a vector space, a Banach space still. Suppose that these functions have continuous derivatives And also suppose that the norms of these functions add up to something finite. So that's like in the m-test, except I have the derivatives here. Make the additional assumption that the sum of f sub n t naught converges for some t naught in my interval. Right, so this, if true, means that the sum of the f sub n's is a continuous function. It's differentiable with continuous derivative, and its derivative is given by the sum of f sub n prime. Right, so that's a criterion for differentiating series of functions. We're going to apply it to power series in a little bit. But the proof of this uses an important fact, which is sort of clear from what we argued last class. You remember, we defined this operator that takes a continuous function in this space, right? Continuous from AG to W, and this gives the integral from t naught to a certain t, or the indefinite integral, right? So this integral takes a function g and computes a new function g here, ig. And we know that the integral is linear. We also have this estimate for the integral saying that the integral is at most the sup of the function inside times the length of the interval. So it turns out that you can show, and then if you can see, it's a nice exercise. This defines a linear and bounded, and therefore continuous, operator on the space C, right? C is a Banach space, and this is a bounded linear operator, and it therefore a continuous operator. Okay, how's this useful? Okay, so I'm just gonna, that's very simple. So first thing is that the condition on the sum of derivatives. So let me call S sub k is gonna be the partial sum, right? Like before. And of course, because if I have a finite sum, our notion of derivative is still additive, right? So I can, for a partial sum, I know that it's differentiable, just because the f sub n's are and the derivative is continuous, right? So now f sub n, the fact that it is finite, means that S sub k prime converges to a certain function that I'm going to call g. Well, that's it's a certain continuous function when k goes to infinity, with g, not g, sorry, g I used before for something else, h, with h belonging to c. That's just the m-test, right? Applied to the derivatives. And I'm saying, well, k prime then converges to something. Okay, so now let's look at what this means, right? So for each n, I have the following: f sub n of t, and for each n and for each t, that's equal to fn of t naught plus the integral from t naught to t of fn prime of u du. And that's the same as saying that fn is equal to this constant here, fn t naught, plus the integral, this integral operator of fn prime. And by linearity, I have that sk is equal to sk of t naught plus I of sk prime, because sk prime is the sum of fn primes, right? So if you add these guys up, you get this one. And sk of t naught is just the sum of the f sub n of t naught. So now, by assumption, we have that sk of t naught converges to a certain value. Right, right, converges to an a belonging to w. And sk prime converges to h in the topology of our vector space C, Therefore, I of sk prime converges to I of h, right? According to the topology of C. Okay, so sorry, let me add a page again. So what do we get, right? So define f to be equal to a plus I of h. So my claim is that if I look at f minus the series, that's equal to a minus the constant skt naught. So, I mean, of course, this means, let me just notice that this thing here means that f of t is equal to a plus the integral from t naught to t of f of u du. So if I look now at the difference between f and s sub k, infinity norm, that's the distance between a minus at sk t naught plus I of h minus sk prime, right? Here I'm using the fact that sk is equal to sk t naught plus I of sk prime. And now I'm just going to break it into parts. Well, I take the norm, the sums at most, the sum of the norms. The first term gives me just a real number, right? These are functions. I mean, if I want to think of these as functions, are a constant and equal to a, constant and equal to sk of t naught. So that's just a real number. And then I get I, norm of I, h minus sk prime. And this at most a minus sk t naught plus the norm of the linear function, the linear operator I from C to C times h minus sk prime. And of course, everything here goes to 0 because we know that sk prime converges to h. We know that sk of t naught converges to 0. So the conclusion is that sk, which is a sum, and goes on to n, of f of n, converges to f in the topology of C. And f has to belong to C. It's a continuous function. Well, it's even differentiable, right, from its definition. And what about the derivatives, right? sk prime converges to h, but f of t is equal to a plus t naught t f u du. Oh, sorry, h u du. This should be h2. And from the fundamental theorem of calculus that we proved, we know how to differentiate f. We just take, well, a is a constant, so we just differentiate the integral. F prime equals h. So not only have we shown that the series of functions converges to the series of functions converges to f, but the series of derivatives converges to the derivative of f. And that's all we needed, right? Because we wanted to show that f, the limit, exists, and that its derivative equals the sum of the derivatives. Well, that's just here the limit of sk prime when k goes to infinity, which is this h that we defined. So we're done. To recap, so what did we use? We used the fact that, first of all, the series of derivatives has to converge somewhere, right, to this h. Second, we use the fact that integrating is a continuous operation and linear. So the sk equals sk at a point t naught plus the integral of sk prime. Since sk prime converges, this value here converges, then everything converges. And the limit is this function here. And then we argue that not only sk, right, the partial sums converge to f, but also the partial sums of the derivative, they converge to h, which is the derivative of f. And therefore we're done. We know how to differentiate this series under this strong condition. Well, as I said, it's a strong condition, but it is sufficient for at least one nice application, which I'm just going to sketch. So remember this power series setting. Now I'm looking at C interval to R. So the A sub n are real coefficients. We remember that if the lim sup of absolute value of A sub n raised to 1 over n is less than 1 over R, then this expression on the top defines a continuous function in this space. Now, if we try to differentiate it, there is an almost irresistible formula, which is what we do in complex analysis, right? We differentiate term by term. So I take the derivative, I get n t minus t naught n minus 1 for n greater than 1. And this is what we have over here, but instead of summing from n equals 0 to infinity, and then I get this formula. So how do I prove that that's indeed the derivative of f? Well, I have to take these guys as the functions f sub n. Well, sorry. These guys are the functions f sub n. These guys here are the f sub n prime, maybe up to a choice of index. And then I have to check, okay, so I have this power series here, which is my natural candidate for the derivative. And what I have to show is that the sum of f sub n prime, the sum of the norms, converges, so that I can apply term 2. But this I know for a kind of interesting reason. So here I have a new power series with these coefficients, n plus 1, a sub n plus 1, which I call b sub n. It turns out that the lim sup of b sub n raised to 1 over n is equal to the lim sup of a sub n raised to 1 over n. So whenever the first series, the one on top, converges, the one at the bottom converges to, and satisfies the conditions of the m-test. And with this and a little bit of thought, we can show that indeed the derivative of the power series is what you expect if you differentiate term by term. And with this I finish. Thank you.